Right, so today's lecture is on partial derivatives of functions. Why it's called partial derivatives? Because this is a derivative with respect to a variable.
So what would be the grades for the previous quiz available?
Oh, you haven't seen it? I have a grade that she's doing that. He's doing that for me. Let me contact him, okay? Because the first time, maybe have some trouble for him. So I will do that. Okay, right after lecture. I did not pay attention to this. I thought it's already posted. Okay. But it took us a long time to change the file name for each of them. So today, when I give a quiz, I already have instruction on the top. So when I receive the email for me, I can quickly save to my computer. So I wish you just send it to me directly to my email address. I post that. So then I just click save attachment, then go to the folder, and it only take a few seconds. Otherwise, have to download it from Canvas, then rename it, then have to look at your name first. Who is this? Usually the file name is a stranger name. Then have to open the file, look at the page, and then find out the name on the top, and then rename it, because otherwise we cannot find it quickly in the future. So that takes pretty much time if you have many students. Okay, so in the future, I hope you can use the same format to send me an email. I send me the quiz. All right. All right. So today we're going to talk about partial derivatives. Okay. Partial derivatives. How to define it? Okay. How to define? So given a function, let's go to that. Given a function of two variables f, x, and y, okay, and define on a domain D, which is in R2, right? Is in plane. So here's a picture. This is x-axis, or it's y-axis. This is my tip, and here's the domain D. Okay. Now, at point x and y, the partial derivative f of x with x and y, okay, is defined to be the limit of this. This is with respect to x. So just some change in the x variable. That's the same y variable. Okay, divided by h. So here we view y as a constant, and then just differentiate the function with respect to x, roughly speaking. Okay, similarly, you can do the same, define the same. Here's a y plus h, fxy. Okay, so here we view x as a constant. It's the independent variable. Then we differentiate with respect to y variable. Okay, so that's it. The definition is very simple. It's called a partial derivative with respect to x when the partial derivative with respect to y. Okay. So if you have a function with two variables, like a f of x, y, it's 1 minus x squared minus 2 y squared, for example. Okay, I just give an example. So this is a function. This is a function in two variables. So let's find out the partial derivative of f with respect to x and the partial derivative of x with respect to y. So remember, when you try to find the partial derivative with respect to x, you view y as a constant, okay? And then, so it's very simple. Just differentiate each term with respect to x. And the first term is going to be 0. Second term is 2x. The third term is not going to be 4y, okay? It is going to be 0 because y is a number, independent variable. Nothing to do with x. So when x changes, y does not change. So the derivative is going to be 0, right? So the derivative is 0. Unless you told that y variable depends on x. Otherwise, y is an independent variable. So nothing to do with x. So no change in y when x changes. That's why the derivative is going to be 0. The meaning of the derivative is the rate of change, right, of this variable with respect to another variable, right? So finally, you simplify it, just make it 2x. Now, the partial derivative of the function with respect to y, and that is going to be 0 and minus 4y, okay? Similarly, because the derivative of 1 is 0, derivative of x squared 0, derivative y squared will be 2y, so that's why negative 4y, okay? That's it. So this is about just the derivative of a partial derivative. And okay, so we can look, then let's take a look at another example. So we'll practice, okay? So this is let's see, find examples from the book. Okay, then and then also we have some other notations that have to get familiar with them. Okay, so given the function, okay, like the square root of 3x plus 4y, for example, right? And we want to find the partial derivative with respect to x and with respect to y. Okay. All right, so the function can be written as 3x plus 4y to the power 1/2. Okay. Right, so use a chain rule. The partial derivative of y with respect to x. So you look at this, right? This is a square root, right? It's, so first, by the chain rule, you have to write this, right? It's minus 1. Okay, 3x plus 4y. Then you differentiate the inside, the function inside, the expression inside. So 3x plus 4y. When you differentiate 3x plus 4y, the first term will be 3, the second term will be 0. Okay. So the first step, you write down like that. So it's very clear to me how do you do it. Then you simplify. Okay. Then you simplify. You have 3 and 1/2 is 3 over 2. 3x plus 4y and then negative 1/2. That's enough. Okay. Now, if you want to use a traditional notation, then you can express in this form. Okay, that's okay. Doesn't matter. Okay, which way. All right. So similarly, the partial derivative of the function with respect to y, you will get 1/2 3x plus 4y, 1/2 minus 1, and here the first term will be 0. The second term will be 4. Okay. Then 4 divided by 2 is 2. Then 3x plus 4y, negative 1/2. That. Okay. Okay, so let's pick up more problems from them. Okay, now if we are given x and y, this is a strange function. Okay, x to the y. Okay, now this is, you have to be very careful about this one. Okay, we want to find the partial derivative. The only formula we can use here, if you have a to the x, that will be a to the x natural log of x. Okay, that's a derivative. If we have a derivative of x to the power n, that's n x to the n minus 1. And here we are assuming, don't need to say anything. N is arbitrary number. So, but if x to the y, both the variable changes, so be careful. You cannot, okay? Let's take a look at, okay? So when you find, when you're trying to find the partial derivative with respect to x, which one you have to use? I think if you want to find the partial derivative with respect to your view y as a constant, if you view y as a constant, then you use this formula, okay? Use this formula, okay? This is the first formula, that's the second formula. So use the second formula, okay? By the second formula, because y is a constant, so it's just y, x to the y minus 1, okay? Now, if you want to find the partial derivative with respect to y variable, x is a constant. So just like here, a, right? So you have to use the first equation. So you will get x to the y and the natural log of x, okay? So here x is constant, just like an a. Okay, so be careful when this is a pretty tricky problem, okay? So you get two different partial derivatives. Yeah, you get two different partial derivatives. Okay, let's take a look at another example. Here's another example. There's f of, this can be any variable, right? So this is let's use the x and the y here. So integral from x to the y, and here t squared plus 1 dt. Oops. Okay. Right, we want to find the partial derivative with respect to x and with respect to y. So we have to recall the formula. The formula says that if you have an integral, and this is constant, this is x, f of t dt, this is going to be f of x. Okay, this is a formula we have. Okay, so we have to do like this. Okay, using the formula. So now I'm going to find the partial derivative. If I want to find the partial derivative with respect to y, that's much, just apply the above formula because x is constant, right? Y is a variable. So look at this formula. This should be equal to just y squared plus 1. Okay. But in order to find the partial derivative with respect to y using the above formula, I needed to express it in this form, negative and yx. I have to put the x on the top. So now y is a constant, x is variable. So when I differentiate with respect to x, then you can apply the above formula. The negative sign is still here. All I have to do is move y is a constant. Okay, it's not variable. So you move x to the x t. So just the x squared plus 1. Okay, so you see it's slightly different. Okay, it's a slightly different. Okay, that's good. And now we let's take a look at another problem. Okay. So now we're going to introduce some notations. We're going, some notation. Okay. As you can see that this is a new function, a new formula, right? So f sub x is actually another function when you differentiate, right? When you get a derivative f sub x, this is the partial derivatives are functions. Okay, partial derivatives are a new function. Okay, this is a type. Sometimes we can, here's a notation, right? Remember, if a z depends on x and y, okay, right? So we have some notations, and this z, okay, then this notation means f of x, okay, and this notation, this is a new variable, okay. So z is a variable. Here's z equals f of xy means you have three quantities, and three quantities. Z depends on x and y by this formula. So z equals that, okay? So the partial derivative of z, so this notation means we call it a partial derivative of z with respect to x. That is the rate of change in z with respect to x. So that is given by this formula, and we already defined that, right? And we also have this one. Okay. Those are the notations. If we have to name the variables, instead of x, y, y1, x2, y2, in that case, and if we label them, let's see, this is a notation we should get familiar with, and then if a function is given by x1, x2, So let's see. So we instead of xy, we use this. Okay. In that case, sometimes we denote just f1. Okay, denote f1 as a partial derivative of x1. Okay, we don't need to keep writing x. Okay, so f1 means the derivative was the first partial derivative was the first variable. f2 means the partial derivative was the second variable, x2. Okay, of course, you can also just you can still use xy. Okay, then f1 means if you use xy, f1 just means x, the partial derivative with respect to x. Okay, so don't be confused about this notation. Just for simplicity, we instead write y and just write f2. Okay, so f2 is a partial derivative with respect to y variable. Those are the notations, and sometimes we also use this notation, d1f. Okay, d1f means f of x1. Okay, and the d2f means the derivative, partial derivative with respect to f2. Okay, so but we try to focus on one notation in this book. We don't want to use all different types of, but when you look at it, if you look at other textbooks, maybe you see different notations for the partial derivatives. Okay. There is a very important theorem. Let's look at some examples first. Then you can get high order derivatives. Okay. So if a given function f, f has x, y, right? So you can differentiate with respect to x, y, and you also get differentiate with respect to y variable. So you get two functions right now. But each two functions, you can continue. F sub x is another function, right? So basically, if you have a function, then you can get the first function with partial derivative with respect to x, and another function partial derivative with respect to y. But this is a new function, two variables, so you can continue partial differentiate. You get xx, right, and fxy, okay? Right, and this one would be fyx, that would be fyy, okay? Because that's the second derivative, and they keep going like that. It's like a tree, okay? So you can do this fxx, right? Then here fxxy, and this will be like a fxyx, and that will be fxyy, for example, okay? So I'm not going to go through the third order derivative, just pass second order derivative. Okay, second order derivative. Okay. Okay. Right, so let's take a look at example on some example. Let's find an example from the book. Well, for the simplicity, we probably begin with a polynomial. Okay, I got x to the fourth power and 3x squared x cubed y, and 5x squared y, and 4x y cubed, and 7y to the fourth power. All the terms, possible terms. You already find that, right? 2, that's a square. Okay. So this is a homogeneous polynomial xy variable. All right, let's do some computation. So you do some computation. fx, right? It's going to be 4x cubed, right? Then this will be 6x squared y, right? Yeah, keep think y as a constant. And this will be 10xy squared. And this will be 4y cubed. And the last term is 0. Yeah, the last term is 0. because it's independent of x variable. Then let's take a look at fy, f sub y, this partial derivative with respect to y variable. The first term will be 0. The second term will be just 3x cubed. And this will be 10x squared y. That will be 12xy squared, okay? The last term is 4 times 7, 28 cubed, okay? So that's again another polynomial, right? So let's continue. Yeah.
And the f of x in the second line, the second variable, you said 6x squared times y. Shouldn't
that should be 9. Yeah, should be 9, right? Yeah, 3 times 3 is 9, yeah. Right? Right. So now let's continue to differentiate. Okay, let's continue differentiation. So we differentiate the function. This is a partial derivative with respect to another function now, right? So you differentiate with respect to x. Okay. So you get 12x squared and 18xy and plus 10y squared. Only 3 terms survive. Okay. Then you differentiate with respect to the same function with respect to y. Then you get the first term is 0. The second will be 9x squared. The third term is 20xy. Then here's 12y squared. Okay. But now we switch to the second partial derivative, f sub y, and I'm going to differentiate with respect to x. So with respect to 9x squared and 20xy and 12y squared. Okay. Then I differentiate with respect to y, so I get double y here. The first term is 0, second term is 10x squared, and the 24xy, and well, the last one I have to do the multiplication. 28 times 3, right? 28 times 3, 28 times 3, 84y squared. Okay, so you will discover that after do several examples, and these two are the same. Okay, that means the partial derivative can the order, can be switched. Okay, we conclude that fxy is going to be f sub yx. So that means in the future, if we find the partial derivative with respect to x and with respect to y, and you also get the partial derivative of the function with respect to y first and with respect to x second. Okay, so this was discovered by the guy who, it's earlier. So that's his theorem. Okay, that was a condition. Of course, it's not always true. And here, let me state the theorem. Okay, this is discovered by him. Okay, we have to assume that f is suppose that f is defined on domain D. Okay, not necessarily this, called domain D, containing the point A and B. Okay, we also have to assume that the partial derivatives are continuous. Otherwise, it's not true. Okay, if fxy and fyx are continuous on D, then we always have this property. Right? You can switch the order. Sorry, it's yx and B. Okay. It's there. Okay. So of course, our partial derivatives of polynomials are always continuous. No problem. That's guaranteed.
Would you mind following up?
Hmm?
I have questions regarding those you have underlined and the red line.
Yeah.
So what do you mean by fxy and fyx?
All right. All right. So let's see. You see, so there's a difference. Okay, what f is just a name of the function. Okay, this is just a name of function. So the name of function. So the given the formula for the f of xy is a formula for the function. Okay, so sometimes we write xy here, sometimes we don't write xy here. Okay, just put f. So using the formula, I get this partial derivative. So this function, this is a formula. Then so the new function we simply returns f sub x. Okay, that's just a name. The next generation. Okay, so f sub x is the name of the new function. It's called partial derivative function with respect to x. What is given by the formula, by this formula. So if this is a x, if this is x squared plus 2y, then that will be 2x. Okay, so we don't want to always write the variables there. Then we just simply write f. But suppose f is defined, f is a function, define that. I did not mention the formula. Okay, there's no need to keep mentioning that. And then f sub xy is a function, is the name of the function from the partial derivatives we obtained from partial derivative. So you have x, xy, that means the formula is given by this formula. Okay, this in this case is 0 actually. Okay, so this is just a name of the functions. Okay, and here's the formulas of functions. So there's a small, there's a little difference between these two notations. Okay, when we do, sometimes we don't want to mention variables. When we mention variables, basically we're talking about the formula of the function. Okay. Sometimes.
Are you saying the f of x parentheses x slash y?
Yeah.
That's the derivative in respect to x, and the second one fxy parentheses. That's the previous the previous function.
Different. Yeah, that's right. So you get this function, right? And when this function, you can still differentiate. But you can differentiate with respect to x, you can differentiate with respect to y variable. If you differentiate with y variable, my next, the notation for the next function would be f sub xy, okay? Yeah, just the generation by generation, you get more and more functions, okay? Yeah. One single function in two variables, the next, after differentiate it, you get two new functions. They both are called derivatives, but they are partial derivatives because the derivative with respect to one single variable. Right, so that's on my picture here. Go back to the picture, I say that, right? Yeah, here I just use the f. I do not mention x, y variable, no parenthesis x and comma y, and because for simplicity, I just want to talk to the function. But the function, the first generation, you get f sub x, f sub y. Okay, those are the partial derivatives. How to define them? You need a formula. Okay, the corresponding formula will be f sub x and parenthesis x and comma y. Okay, so then those are new functions. You can also differentiate because that depends on x, y. Just repeat the same procedure, but each of them you produce two more functions. Okay, so just a double each time. Okay, so you can get more. Okay, but we find out we actually do not get the four different functions. It turns out to be those two are the same. Okay, so the next generation, actually you only get, in general, you only get 3 different functions instead of 4, because the theorem says that f sub xy is going to be f sub yx. Okay, and there are many actually. Now the third generation, I believe that those two will be the same. Okay, yeah, those two will be same because there was a double x one y, double x one y. Okay, you can interchange the order in for many functions. Okay, as long as the function is very nice functions, it's always true. Okay. Right, so we can those are the partial derivatives. Yeah, we can check it using different functions, not necessarily polynomials. Okay. We can, yeah, let's look at another example. Yeah, let's look at problem number 54. And this is a pretty strange function. It's natural log ax plus by. Okay, ax plus by. Ax plus by. Okay, I want to find out the first order partial derivatives, the second order partial derivatives. Okay, so this is a derivative with respect to x and y. And so I get, using chain rule, you get ax plus by, then the partial derivative of the function inside with respect to x, so it's a. Okay, then I have similarly, I get this time is b. Okay, so now let's continue. It's now a little bit difficult, right? It's a fraction. That's okay, right? So fx, the partial derivative with respect to x. If you write this like this, ax plus by and to the negative 1, that's much easier. So it will be negative a, ax plus by, and negative 2, right? Then the derivative of the inside function with respect to x, I get a. So that's a squared, okay? Then you have a partial, differentiate the same function, above function with respect to y. I get a negative, here's a. Then here's ax plus by, negative 2. Then you differentiate inside with respect to y variable. You get b, not a, so we put ab. But similarly, you can do this one. X, y, x, right? Is a partial derivative of f sub y with respect to x. So this is the same as, you can write as b and parentheses negative, right? So first of all is negative, b, then that'll be negative 2, but you have to differentiate inside. So it's a derivative with respect to x, so you get an a. Okay? And then similarly, let me just simply write the answer here. It's negative b squared x plus by negative 2. All right, so look at this 4. You find out those two are the same. Okay, a and b equals b and a. Okay, so we verify the theorem again. Yeah. Now, how did the mathematician discover that? Usually after you do enough exercise, and you should immediately realize, oh, this should be equal. Then you try to prove it. Once you prove it, and then you publish a paper, then this become a formula, right? You call the theorem. Right? This is the same thing like in biology. If you do experiments and something shows up, similar thing shows up, always. Then you do more experiments, and then you test it again, and you find that it's it. But the biology is different from mathematics. After they repeat the same experiments several times, then they jump to the conclusion. That's it. This is called science. But there's still a small possibility you know, in the future, 10 years ago, people find out, no, this is not the case. Some other samples find out it's different. You cannot jump to different phenomena. You cannot jump to this general conclusion. Okay, but the mathematics, if we prove that is true, that's always true. Okay? It don't need it to be revised. So, so mathematics is different from science. Okay? That means the textbook don't need to be revised. You can still use the textbook used by grandfather for the calculus, and you still can learn the same material. Okay. Now, why you get a new textbooks, heavier, right? It's 2 pounds or 3 pounds, and that's just a commercial purpose. Okay. In my opinion, yeah. Okay. And possibly the textbook used by grandfather is much better, light, maybe. Okay. But the quality of the paper is not good. Okay, that's true. Okay. Right, so they're equal, right? So we verify this theorem, those two are equal. Okay. We can also look at another problem 60. Okay. Now this is let's say let u to be e to the xy and sine y. This is a quite different function, right? Now,
What's after the x of y?
E to the x times y, and then sine multiplied by sine y. Okay. So this is so you have 3 variables, u and x, y. Okay. Okay. Now we have to. So what is our notation? Yeah, let's use this notation. Let u represent this expression, and then this notation will be like that. Okay, partial. Okay. So this is confused about notation, right? So this means a partial derivative of u with respect to x, then you just differentiate the expression, okay? So here is there's only one term containing x. So let's differentiate. You will get y, e to the xy, and sine y, okay? Why? Because you view y as a constant, so when you differentiate, you take the y out. So this is our formula, right? Kx, that's k e to the x, right? Kx. Yeah, k is a constant. And you can differentiate u with respect x and then respect to y. That's our notation, x and y, okay? So in actually, this is going to be x, okay? Differentiate this new quantity with respect to y variable, okay? So we can learn this kind of notation through the examples. All right, now this time, it's y sine y, right? E to the x times y, okay? So now how many y variables? We have 3 y variables, okay? One, this term, that term. So you apply the product rule. The first term you get derivative of y, right? So it's sine y e to the xy. Then you differentiate sine y. So it's y cosine y e to the x times y. Then you differentiate the last term. The derivative with respect to y variable, so x should be taken out. So xy sine y e to the x times y. So you get 3 terms. Can you simplify it? Well, maybe. So there's only one common term, e to the x times y. Okay, so you can, if you want, you can take this out. Okay, make it easier. Sine y plus y cosine y plus x times y sine y and e to the x times y. Okay. That's a partial derivative with respect to x and respect to y. So now let's take a look at the partial derivative of u with respect to y variable first. Oops. Okay, let's go back. Why it's gone? Okay, it does not hold. Okay, let's disappear. Okay. Yeah, this is a partial derivative with respect. Let me keep this term here. Sine. Okay. Right, so now it's a partial derivative with respect to y variable. So this time we already have 3 terms already, right? So the partial derivative, let's write here's y, e to the x times y. No, that's only 2 variables. There's no y here. Okay, so you apply the product rule. You apply the product rule, the first term, you will get x e to the x times y. The second term is cosine y, okay? So view x as constant. Then you differentiate with respect to x variable. So now x is after the y variable, right? So when you look at this, you have to apply the product rule here. So it'll be x e to the x times y. And then you differentiate x with respect to y variable. So you get x times y, e to the x times y, sine y. Okay, so you get those 2 terms. And here, I'm going to differentiate with respect to x. So only this term I should be careful. Yeah. So with respect to x, so y should be out. Okay, so you also get 3 terms. When you compare those 2, you realize that they're the same. Okay, you can take out sine y, and here xy, sine y, and here y, cosine y, e to the x times y. When you compare those 2, I think that's identical. So your conclusion is, okay, you can conclude, yeah, you conclude this. Okay. Right. Now, why? Yeah, there are many different notations for the functions. Sometimes, yeah, the function. You see, let me repeat it. So you get usually the function f, right? Function f is going to be here. Is going to be the map from here to the line. Okay, this is f. So given x variable, and you get another variable here. Now this variable usually denoted by z. Right. So how do you describe this function? You know, for it assign a unique value to each point in the domain. So this can be can be given by a formula. Okay. So the relationship usually is written in this form. Okay. Let me repeat this again. Okay. It's given by. Okay. Now sometimes simply we just put the formula here. We call it a function. But actually, f of x, y is not a function. It's just a formula for the function. Okay, the function is a kind of like a correspondence, assignment here. To each point, you assign a unique value of z. Okay, now if you look at this relationship, then you can also say that the variable z depends on x and y by this formula. Okay, this is our notation. Okay, so this really means the partial derivative of f with respect to x. Okay, so this really means the partial derivative. Okay, so partial z over partial x is a name of the new variable. Okay, that is given by that expression. Okay, that is given by the expression. In other words, you are going to get, yeah, the same domain maybe. Here's the point xy, and here is going to be fx, okay? And this is a line. Now, the image of this map, and that's going to be the notation partial z, partial x, okay? So it's given by, okay? Okay. Now, why use you see, this is a little bit complicated. Why you do not use another variable? Well, because if you use another variable, it's harder to recognize this is actually coming from the derivative. So the original variable is only one letter. The new variable actually involves three different letters, p partial z over partial x. So it's complicated. It's okay, use more letters to describe a new object. Okay, so that I hope you understand this notations from this picture. Okay, f sub x is a new function. This is actually the partial derivative function with respect to x. Okay, and it assigned a number to each point in the domain. That new number is denoted by this this notation. Okay, and the meaning of this is partial z over partial. We just call it partial z over partial x is the rate of change of z in with respect to x. Okay, is the rate of change in the quantity z with respect to x. Okay, but and sometimes a function is defined implicitly. Okay, we can still find it. Okay, it's a partial derivatives given the relationship. Okay, x squared minus y squared plus z squared equals minus 2z equals 4. Okay. Find the partial z with respect to x and partial z with respect to y. What does that mean? That means we're going to find the rate of change in z with respect to x and the rate of change in z with respect to y. Okay. Right. Right. So now we have so how do I do that? Well, so z depends on, here's the point, z depends on x and y implicitly, okay, by the above formula. So z actually is going to be a function of x, y, but I don't want to write the formula for the f, okay? It's because sometimes it's solvable, sometimes you cannot, okay? You cannot use the elementary function to express it. You can only use an equation like that to describe the dependency. But I still can find the partial derivative, right, of z with respect to x. I still can tell the rate of change in z with respect to x. How can I do that? I can differentiate both sides with respect to x. Okay? Then the left-hand side, look at, okay, the x squared with the derivative of x squared with respect to x is 2x. The second term will be 0. The third term is 2z partial z partial x. And minus 2, and this side is 0. Okay? So clearly, this will be this combined, right? So 2x is going plus 2z minus 1 equals 0. So I can solve for partial z, partial z with respect to x. This is going to be negative 2x over 2z minus 1. After I simplify, I get x negative, right? So I switch the order. So x is over 1 minus z. Now this one, the partial derivative of z with respect to x still depends on z. That's fine. If you can solve for z in terms of x, you can get a formula for this partial derivative, okay, with respect to x and y, okay, a formula. Okay. So we are fine with this, okay, and you can say that where z is determined by the above equation. You can find z, no problem, yeah. So here's x squared minus y squared plus, let me repeat again, plus z squared minus 2z equals 4. And technically you can solve for z. This is a quadratic formula, quadratic equation. Plus x squared minus y squared minus 4 equals 0, right? Z is going to be, by the quadratic formula, it's 2 plus minus b squared minus 4ac. Okay. I can take the 4 out. So actually you get 2, 1 minus x squared minus y squared minus 4. And after I simplify it, I get 1 plus minus, and the 1 minus x squared minus y squared plus minus, it's actually 5. So you get 2 pieces, right? You get 2 pieces. Be careful, yeah. It's not uniquely determined. You get 2 pieces, plus minus. Then you differentiate, okay? So you can get, in this particular case, if you can solve for z, you can find the partial derivative. You get a formula depends on x and y only. But if you use an implicit differentiation, you get another type of formula, but it involves z. Okay, if you find a z, then you can get the derivative. Okay, you can, if you want to, you can put it here, if you want. Okay, but there's 2 possible solutions here. Right, it depends on the sign, plus minus. Right. So let's take a look at another function. Let u to be e to the x sine y. Right. Okay, this is a quantity depends on x and y. Okay, so we have to find out. Okay, this is my notation. This is actually a partial derivative with respect to x. So I get derivative, so e to the x sine y. Nothing's changed. And then I get xx, right? That's partial derivative with respect to x. So I still get the same, no change. Okay. Okay, that will be partial derivative with respect to x, and with respect to y, I get e to the x cosine y. Then I find the partial derivative with respect to y variable. I get e to the x cosine y. Okay, and what? What else? So we have to find this. So I get e to the x cosine y. Okay, the final one. Y and the y. So I get negative e to the x sine y. Okay. All right. So what we can find out? We discovered 2 things, right? If it's first one. First of all, we see that xy equals y. Okay, uxy equals uyx. Okay, they're both equal e to the x cosine y. Okay. This is guaranteed by the theorem. Guaranteed by this theorem. Okay. Now you also see that we discover that we find out those 2 have an opposite sign. So that means u to the xx plus u to the yy is going to be canceled out. They are going to be, that's going to be 0. Okay. And this is interesting. Okay. And okay, we have this type of equation called the Laplacian equation. Laplace equation. Okay, and any solutions to this equation are called harmonic solutions. A harmonic function, yeah. Any solution to this equation, okay, is called a harmonic function. Yeah, we have a special name there. So there are kind of solutions there. These are only particular solution. Okay. So by this definition, u equals e to the x sine y is a harmonic function. That is a final harmonic function. And you may also can find the new harmonic functions. There are some called wave equations, all kinds of equations. Right? We stop here and and we discuss all these partial derivative notations. And I hope you find the time to do the homework. Okay, it's not easy to study math these days. You have to be online. Okay, so let's spend let's take the quiz. Okay, we have more students online right now.